Hey Calculus class, today we're going to learn about topic 58, calculus with polar coordinates. So we're going to start off with derivatives to polar curves. And given a polar curve, r equals f of theta, the Cartesian coordinates of a point on the curve are x equals r cosine theta and y equals r sine theta. That means I can replace r with f of theta. So therefore x equals f of theta times cosine theta and y equals f of theta times sine theta. With parametric curves, we found the derivative by taking the derivative of the y-coordinate over the derivative of the x-coordinate. We do the exact same thing with the polar curves. But this time we're doing it in terms of theta. So if I want to find the derivative of y with respect to theta, I'm going to need to take the derivative of f of theta times sine theta. And then when I take the derivative of the x coordinate with respect to theta, I'm going to take the derivative of f of theta times cosine theta. Now, since these are two functions in terms of theta, we're going to need to use the product rule to find the derivative of each coordinate. So for the derivative of the y coordinate, I'm going to have the derivative of the first function, which the derivative of r, or derivative of f theta, times sine theta, minus f of theta, or r, times the derivative of sine. The derivative of sine is negative cosine, so I have plus r cosine theta, all over the derivative of the x-coordinate. So when I take the product rule of r cosine theta, I get r prime cosine theta minus r sine theta. All right, so let's look at an example. What is the slope of the polar curve r equals 2 cosine 4 theta at any angle theta? So we know that the derivative of a polar curve is going to be represented with r prime sine theta plus r cosine theta all over r prime times cosine theta minus r sine theta. Well, I'm given my function r, so I'm going to need to find the derivative of 2 cosine 4 theta, which will give me negative 8 times sine 4 theta. Now I can go ahead and set up my derivative. So I have the derivative of r times sine theta plus the r times cosine theta all over the derivative of r times cosine theta minus r times sine theta. And I can do some simplifying, so I can factor out a negative 2, and I'm left with the following as my derivative of that polar curve at any angle theta. All right, what is the equation of the tangent line to the polar curve r equals cosine 2 theta when theta equals pi over 4? So first thing is that I need r prime, which will give me a negative 2 sine 2 theta. I can set up my dy dx, and since I want specifically at theta equals pi over 4, I'm going to plug pi over 4 into dy dx. And I'm going to go ahead and simplify. And after doing some simplifying, I get a slope of 1. Now, since I'm writing the equation of the tangent line, I need my x and y values at pi over 4. Well, I know that x equals r times cosine theta. Well, r is cosine 2 theta, so therefore x equals cosine 2 theta times cosine theta. And since y is r times sine theta, I have cosine 2 theta times sine theta for y. So to find the specific point when theta equals pi over 4, I'm going to plug in pi over 4 into both the x and y equations. And after I evaluate, I get 0. So that means I'm looking at the point 0, 0 with a slope of 1. So therefore, the equation of the tangent line is y equals x. All right, now let's look at horizontal and vertical tangent lines. So let's suppose that x prime of theta and y prime of theta are continuous. Then for the curve defined by the polar equation, r equals f of theta, and where c is some angle, we have that if y prime of c equals 0 and x prime of c does not equal 0, there is a horizontal tangent line at the point r of c comma c. So that just means that you have basically the slope equals 0, hence you have the horizontal tangent line. So therefore we can say that if r equals r sine theta, then r prime is equal to r prime sine theta plus r cosine theta using the product rule. And then you would have a vertical tangent line where the derivative does not exist. So therefore the derivative does not exist when the x value equals 0 and the y value does not equal 0. So we have that the x coordinate is r times cosine theta. So using the product rule, the derivative of the x coordinate is r prime cosine theta minus r sine theta. All right, so let's look at an example. We want to find all points on the polar curve r equals 1 minus sine theta where there are horizontal or vertical tangent lines. So if we were to graph this function, we would get this lemicon as our polar curve for r equals 1 minus sine theta. Now you have to go around once in order to get the complete graph. So we know the interval we're working with is 0 to 2 pi. Well, first we need r prime, which will give me a negative cosine theta. So x prime is going to equal negative cosine theta times cosine theta minus 1 minus sine theta times sine theta. And I'm going to set that equal to 0. And I chose 0 because vertical tangent lines occur when the x coordinate equals 0 because the derivative will not exist at that point. So after doing some simplifying, basically I replaced cosine squared theta with its Pythagorean identity 1 minus sine squared theta. So now I have 2 sine squared theta minus sine theta minus 1. Now I can, this is in quadratic form, so I can factor it to be 2 sine theta plus 1 times sine theta minus 1. And I set the sine theta equal to each of the factors. So sine theta equals negative 1/2 and sine theta equals 1. So therefore theta can equal 7 pi over 6, 11 pi over 6, or pi over 2. Now to actually find the points where these vertical tangent lines lay, I now need to find the radius at each angle. So r of 7 pi over 6 equals 3/2. I just plugged 7 pi over 6 into my r function. R of 11 pi over 6 also gives me 3/2. And r of pi over 2 equals 0. Now this is only where the vertical tangents lie. Now we need to find where the horizontal tangents lie. So that means I need to take the derivative of the y component and set that equal to 0. Do some simplifying. I can factor out a cosine, set each factor equal to 0 and solve. So cosine theta equals 0 is when theta equals pi over 2 and 3 pi over 2. Sine theta equals 1/2 is when theta is pi over 6 and 5 pi over 6. All right, I'm going to do the same thing that I did with the vertical tangent lines, finding the r value at each angle. So r of pi over 6 equals 1/2, r of 5 pi over 6 equals 1/2, r of pi over 2 equals 0, and r of 3 pi over 2 equals 2. So that means my vertical tangents occur at these points on the polar coordinate grid, and the horizontal tangents occur at these points on the polar coordinate grid. All right, so if we were going to look at these graphically, our horizontal and vertical tangents would lie at only 5 of the 7 points. So basically, if a point works for both, then we cannot make a conclusion. So if you notice, we have 0 comma pi over 2 for both vertical and horizontal. You can't have it be both. So therefore, it actually is neither. All right, finding a point of intersection of polar equations. So if we have r equals 1, which is just your unit circle with a radius 1, and r equals 2 cosine 2 theta, we are first going to set the polar equations equal to each other and solve for theta. So we want to look at which values of theta does 1 equal 2 cosine 2 theta. So therefore, cosine 2 theta equals 1/2. And that means 2 theta will equal pi over 3 or 5 pi over 3. So therefore, theta will equal pi over 6 or 5 pi over 6. So that means I have the points where the radius is 1 at the angles pi over 6 and 5 pi over 6. Now graph the polar curves and confirm you have all of the points of intersection. So after graphing, you should get your two graphs. You have your unit circle of radius 1, and then you have your fun little rose curve with 4 petals. If you look at the graph, you will see that they'll intersect 8 times. 1, 2, 3, 4, 5, 6, 7, 8. So we need to find all 8 of those points. Well, we already found 2 of them, where we have a radius of 1 and an angle of pi over 6 and an angle of 5 pi over 6. So that would represent this point, this intersection point here, and this intersection point right here. Now, since polar curves are symmetric, you can use symmetry to find 2 other points. So that means we would have one with a radius of 1, and we would have the points at the angles 7 pi over 6 and 11 pi over 6. So that would represent this intersection point here, because it's symmetrical with the 1 comma 5 pi over 6 point. And then the point 1 comma 11 pi over 6 is symmetrical with the pi over 6 point. Now that gives me 4 of the 8. Now you can get the other 4 points by using the fact that r can also be opposite. So that means I'm going to take r, but this time make it -1 and set it equal to the other r, which is 2 cosine 2 theta. Solve like I did before. So therefore I have that theta could equal pi over 3 and 2 pi over 3. So 2 more points would be 1 comma pi over 3 and 1 comma 2 pi over 3, which would represent this point right here. There's the pi over 3, and then this point right here, which represents the 2 pi over 3. And then with symmetry, I can find the last 2 points, which will be 1 comma 4 pi over 3 and 1 comma 5 pi over 3. All right, finding the area of a region in polar coordinates. We first need to recall the area formula of a sector of a circle. Let's see how many of you guys remember that from geometry. And that is represented as area is equal to 1/2 times the radius squared times the angle. So if f is a continuous and non-negative function on the interval from a to b, where b minus a is between 0 and 2 pi, then the area bounded by the polar curve r equals f of theta is given by the integral from a to b of 1/2 r squared d theta. So graphically, this is what this would look like. So I'm basically finding this area, the sector, or the area of this sector, but typically when we did that, this was just a beautiful, nice curve for the sector of a circle. But now since this is a funky curve, that's where we're going to use the integration. All right, so let's look at some examples. R equals 3 plus sine theta. So if you aren't given an interval, you will want to graph the polar curve. So graphically, it will look something like this. And in this example, the interval is from 0 to 2 pi, because in order to get the complete graph, the angle goes all the way around the circle. I'm going to go ahead and set up my integration. So I have 1/2 times the integral from 0 to 2 pi of the radius squared d theta. And after, I just used my calculator to evaluate, so I have an area of 29.8451. All right, for part 2, or example 2, we want to find the area of only one loop of r equals 2 cosine 4 theta. So if I was to graph it, I have a nice little rose petal with 8 petals. And to find this interval, you want to find at what angles do one of the loops start and end at. So to start off with, you just need one petal. You can choose any of the petals, but I usually would recommend choosing the one that's along the 0 angle. So I know that it's going to start and end at the origin with a radius of 0. So I'm going to set my radius equal to 0 and solve for that angle. So I'm going to get that 4 pi will have to equal pi over 2. So therefore theta equals pi over 8. So that means that this part of the petal, the top part of the petal, is between the 0 to the pi over 8 angle. The bottom part of the petal is between 0 and negative pi over 8, since they're symmetrical. So therefore I can set up my area as 1/2 times the integral from negative pi over 8 to pi over 8 times, or of 2 cosine 4 theta squared d theta. Now because of symmetry, we can just double the integral and just go from 0 to pi over 8. So therefore my integral will look a little bit nicer. So it will go from 0 to pi over 8 of 2 cosine 4 theta squared d theta. And after integrating, I get an area of 0.7854. All right, now we want to find the area between the two polar curves, r equals cosine theta and r equals sine 2 theta. So first I'm going to graph them. And to find this interval, you want to find at what angles the curves intersect at. So that means I need to set them equal to each other. So I am looking for basically this angle and this angle. So I get one side equal to 0. I can use my lovely double angle formula, factor out a cosine, set each factor equal to 0 and solve. So theta can equal pi over 2 and 3 pi over 2. And sine and the other theta will be pi over 6 or 5 pi over 6. Now if we look at this graph, you notice that it gives us 4 angles, but we only really see 2 intersections. But the 3 pi over 2 and the 5 pi over 6 occur when the curves come back to a radius of 0. So therefore, those angles are not going to help us at all. So we are going to ignore those. So now if I look at where the angle pi over 6 is, which is right here, because that is the smaller of the angles between pi over 6 and pi over 2. And then of course we have our pi over 2 angle, which is right here. So we basically want the area between the curves from 0 to pi over 2 and then from 0 to 3 pi over 2. Now since it's symmetrical, if we can just set up one of them, we can just double the integral to get the total area. So since this is intersecting between the 0 and pi over 2 at pi over 6, we're going to have to set up 2 different integrals. So the first integral I'm going to set up is from 0 to pi over 6. And when I do that, I have 1/2 times the integral from 0 to pi over 6. And when I'm doing that, the only curve that actually is part of is the sine 2 theta, which is the green curve. So I have r squared. then I'm going to add the area between pi over 6 and pi over 2. So I have 1/2 of the area from pi over 6 to pi over 2. And this time I'm working with the red curve, so I have cosine squared d theta. Now, because of symmetry, like I said earlier, we can go ahead and find the area of one piece and double it to get the area of both pieces. So therefore, I have this integral for only this piece of the curve, and I'm going to double it to get this piece of the curve. So after simplifying, I get the following, and using my calculator, I get the value of 0.4606. All right, now let's find the area that lies inside r equals 1 plus 2 cosine theta and outside r equals 2. So graphically, here we have the green curve represents the circle with a radius of 2, and then the red curve represents the lemicon of 1 plus 2 cosine theta. So in this case, you'll want to find the area of the outer polar curve, then subtract the area of the inner curve. So we're going to take 1/2 of the integral from a to b of the radius of the outer one squared minus the radius of the inner one squared d theta. And when you're looking at this graph, you should notice that the outer curve is the red curve because it's going outside of the green curve. So we know that that's going to be our outer one, and therefore the green is our inner curve. But before we can do that, we need the limits. So I have that r equals 2 and r equals 1 plus 2 cosine theta. So I can go ahead and set them equal to each other. And then I'm going to solve for theta to get that theta can equal pi over 3 and 5 pi over 3. Now, since 5 pi over 3 is the lower limit, because 5 pi over 3 is right here, we are going to want to use negative pi over 3 for when we set up our limits. So that means I am looking at the area that lies inside of here, but outside of r over 2. So I'm looking for this area right here where my arrow is moving back and forth. And I'm going from the angles negative pi over 3 to pi over 3. So when I set up my integral, I have half of the area from negative pi over 3 to pi over 3 of the outer radius squared minus the inner radius squared, d theta. And I can go ahead and simplify and then evaluate. And after I've evaluated, I have an area of 3.2829. All right, now let's look at arc length in polar coordinates. So the arc length of a polar curve r equals f of theta, where theta is between 0 and b, is given by L, representing arc length, equal to the integral from a to b of the square root of r squared plus dr d theta squared d theta. So for an example, find the arc length of the curve r equals sine squared of theta over 2 on the interval from 0 to pi. So we need the dr d theta, so I need to take the derivative of r using the chain rule, and then I can set up my integral. And yes, we can just plug this in our calculator to get our value, but this is something that we can take the integral of. So I'm going to go through that process to refresh our memory of some integration techniques. So first thing is I can go ahead and distribute through the powers to get the square root of sine to the 4th of theta over 2 plus cosine squared theta over 2 times sine squared theta over 2 d theta. So now I can factor out a sine squared theta over 2 to get the following. And I can take the square root of this sine squared to get sine theta over 2. And if we notice right here, this is our Pythagorean identity, which will just equal 1. So therefore I can rewrite it as the integral from 0 to pi of sine pi over 2 times the square root of 1 d theta, which of course just reduces to sine pi over 2 d theta. Now when I integrate this, I'm going to use u substitution. So u equals theta over 2, du equals 1/2 d theta. I just am missing a multiple of 2. All right, so now once I set up the integral in terms of u, I also change my limits. So now I'm going from 0 to pi over 2, and I have 2 times sine u du. And now I can go ahead and integrate that. So I get negative 2 cosine u, and I'm going to evaluate it from 0 to pi over 2. And when I do that, I will just get 2. Well, I hope you enjoyed learning the calculus of polar curves, and I will see you in class tomorrow. Have a good night.